This is problem 6-12. It's on page 277. Determine the force in each member of the truss and state if the members are in tension or compression. Set P1 to 240 pounds and P2 to 100 pounds. So let's sketch the system that's given. There are two connection points back to ground. Both are pinned connections. Actually, I'm wrong about that. Actually, one is a rolling connection, excuse me. There we go. And this rolling supports just behind a pinned connection. How that would work in the real world, I don't know. It doesn't matter right now. Our goal is to analyze this truss system. Now, they are not connected together here. They are connected out here. So these members are connected, but these two cross members are not connected. So we've got point B down here, point C up here, point D, and point A. Now, P1 acts to the right, and that was the 240 pound, try again, 240 pound force. And then there was load P2 at 100 pounds. Some geometry, there's a span of 5 feet between points B and C. There's a span of 12 feet between points A and B, C, D as well. So of course these cross members are 13 feet long. Guess I could put my units in there. If you do the math, square root of the sum of the squares, you'll find that it's a 5, 12, 13 triangle. Free body diagram. We're going to start with the entire truss, as we always do, even though we're using the method of joints to solve this problem, because we need the reactions at the wall before we can do anything else, really. So there's CX, BX, CY. Since B is a roller, there's no BY. Then, of course, our 240 pound force and our 100 pound force that act to the right and down. So what I will do is begin by summing moments about point C, taking counterclockwise as positive. What that'll do is get rid of CX, CY and allow me to calculate BX. So 5 times BX, in other words, let's see, we've got a 5-foot moment arm. BX acts about C in a counterclockwise fashion, so that's a positive thing, minus 12 times 100. Well, what's that? Well, 12 feet is the moment arm of the P2 100 pound force, and that causes a negative moment about C. Why not the 240 force? Why isn't that in there? Well, because it passes through C. We don't need it. So this sum comes out to 0. Those are all the moments. And what this does is yield BX. Just take 1200, divide by 5, and that is BX. That comes out to 240 pounds. So let's put that on our free body diagram, or better yet, let's put it over here. 240 pounds. I'll just put the reactions here. And then if we sum forces in the horizontal direction, we have, of course, CX, BX, but then we have the 240 pound force that acts at the right side at D. And so since BX is a positive 240, there's also 240 at P1. Then what that means is that CX, by the way, this has to sum to 0, CX must be negative 480 pounds. So we figured out the magnitude of the force in the horizontal direction. And it's actually in the other direction, but I'm just going to leave it, the arrow to the right. That's the way I drew it on the free body and right. Negative 4, if I can write. Can't write and talk at the same time. There we go. 480 pounds. Finally, if we sum forces in the y direction, well, we find that we've got CY acting up and the 100 pounds acting down, so why even bother writing it down? I mean, after all, it's just going to be CY minus 100 equals 0, therefore CY is equal to 100, so it's pretty easy. So the amount of force up at pin C is 100 pounds force. So the whole point of that whole free body and all those equations was simply to get the reactions, but what they asked us to do was to determine what the force in all the bodies, force in all members stay whether they're tension or compression. So we got what? 1, 2, 3, 4, 5 members to deal with. So using the method of joints, what we need to do is find a joint that we could solve. So for example, if you look at joint D, we know the two external forces applied at point D, and then there are only two members. Since we have two equations with the method of joint, sum of forces in X, sum of forces in Y, and there are two unknown forces because we've only got two members, and remember these are two force members, therefore we know the direction of the force, then the only two unknowns that we really need to solve for there are the magnitude of those two forces. So let's make a free body diagram of point D and then solve it. So we've got the externally applied 240-pound load, the externally applied 100-pound load, and I'm just going to draw the force in CD and the force in BD as tensile forces. I don't know that they'll come out that way, it doesn't really matter. What matters is that I solve for them. If they come out negative, then I guess the wrong direction. All right, so should we begin with sum of forces in the X or Y? Well, if we sum forces in the horizontal direction, notice CD appears in it, and there is a horizontal component of BD. But if we sum forces in the Y direction, BD is the only unknown force that has a component in the Y direction. So it would be wise to start with sum of forces in the Y direction. The most obvious one is the negative 100-pound force that's externally applied. But BD also has a negative force. Let me write this in the way. Negative BDY. Whatever the Y component is of BD, well, the way I've drawn it acts downward. So let's expand that just a little bit. And let's write it in terms of geometry. We know the direction of that force. If we want the Y component of it, well, it's a similar triangle. The force triangle is similar to the geometry triangle. What do I mean by that? Well, look at the geometry triangle. 5, 12, 13, right? And there's a right angle here. This is point C, point D, and point B. Well, all I'm saying is that the force BD has to act along a line parallel to that hypotenuse, right? So if I want to break it up into vertical and horizontal components, I didn't draw that very well. They don't look very similar. Let me try again. That's a little better. If I want to break BD into horizontal and vertical components, since it is a similar right triangle to this geometry triangle, well then I can use the ratio of the sides of the geometry triangle to scale the force triangle. So if I want just the Y component, well that's right here. And so the ratio BDY over BD would be 5 over 13. Or in other words, if I have BD, but what I really want is BDY, just take 5/13 of that. Okay? So what I've done is I've made the force triangle similar, or used the fact that it's similar to the geometry triangle, to infer the magnitude of BD. So BD then would be, let's see, we'll pull the negative to the other side, pull the negative sign, or pull the 100 to the other side, pull the negative to the other side, and we'd have minus 100 times 13 over 5. And so if you do the math, that comes out to negative 260 pounds. So let me make a table over here, I guess. Put load, or better yet, let's put force and tension or compression. We'll just make a table here. We've got 5 different members. And you know what? I guess I should move that down. BD is one of them. We'll get CD next, because of course we'll use the sum of forces in the horizontal direction with point D. A little preview of what we're going to do next though. I then moved to B down here. And I will get from that BD and BA, and then finally we'll get CA at the last. So we know the force in one of these members. I'm going to write it in terms of magnitude. What did I say this comes out to? This comes out to 260. Of course, these are all pounds force. And since it's a negative sign and I assumed that it was tensile, then I got it wrong. This must be a compressive force. You see? Now, when we sum forces in the horizontal direction, I'm going to plug in BD as a negative thing, because I know that I will use the direction that this suggests, that my free body diagram suggests, but I know that in that direction BD is a negative thing. So let's sum forces in the horizontal direction. What do we get? Well, 240 is the obvious one, minus CD. And then minus BDX. Okay? Now let's expand that just a bit. In fact, let's expand it and solve for CD at the same time. So moving this to the other side, 240 minus BD, but BDX, well, what would it be? Well, it'd be 12/13, wouldn't it? Looking at the similar triangle, the similar geometry triangle to our force. So there we go. So we know what BD is. So 240 negative. Now this negative sign comes from the equation because I've assumed a negative direction for BD, but I know BD itself is a negative 260, so I need to put in negative 260 12/13. Okay? And once you go through the math, you will find that CD is 480. That's what this comes out to. Now it comes out to a positive 480, not surprisingly, negative times negative is positive, and therefore this is a tensile force, just as I suspected. Okay? So we've got the magnitude of the force in two of the members. What point should we go to next? Well, we have options. We have A, we have C, and we have B. If we go to A, you might say, well, there's two members there. That looks the easiest. If we go to A, there are no external loads at A, are there? In fact, since there are no external loads at A, well, let's see, then that would mean we've got, let me put A on the other side. That would mean we've got force BA and force CA. Well, if we sum forces in the vertical direction, CA is the only contributor to that force equation. And so it can't be balanced by anything else. Therefore, CA must be 0. And if CA is 0, basically if it's gone, then the only force would be force from BA in the horizontal direction, but that can't happen either. So what we just proved by point A is that BA and CA are both 0. That only leaves, so it doesn't matter if it's tension or compression, there's no force in those two members at all. The only other points we could select are points C or B. Now if I select point C, I actually went to point B next. The reason I didn't actually go to A. The reason I didn't go to C is because I saw this member and saw that there were 1, 2, 3 potential terms in the equation. And, well, I guess that's the same as going here. I guess for whatever reason, I just recognized there would be no force in this lower member and said, well, that means I'm going to end up with, an external reaction as well as two forces, and so it seemed easier. So I went to B, although C would be just as easy. Anyway, so point B, we'll have forces like this. Let's see, CB, BD, and BA. Now we've already shown that BA is equal to 0. So we may as well not even draw it, right? Because since this is 0, well, it's not even there. And, oh, let's not forget, there's a 240-pound reaction force at B as well. And so what we could do is calculate BD, because look, we know a horizontal force, so we should be able to get at the horizontal component of BD. So summing forces in the x direction, we have 240 plus BD x equals 0. Notice that I am again assuming that BD is a tensile member when I know it's actually compressive. Okay, if I drew my arrow in the other direction, that would be fine. I would just have to plug it in as a positive thing instead of a negative thing. As it is, remember, in my mind, I keep remembering that BD was negative 260, and so that's why I left it as a tensile force. That way I can plug in negative 260 and be done with it. But anyway, whatever works for you is fine. Just be consistent. So 240 pounds, BD in the x direction. Well, let's see. We need the x component of this line. So it's going to be 12/13 of the line. Okay. And this is equal to 0. And so, wait a second, I'm missing something. We already solved for BD. Oh, yeah, we solved for BD. What am I thinking? So this would just verify then that BD is in fact 260 and that it's compressive. So that's just a check equation. Summing forces in the y direction should give us CB. I forgot we already knew BD. So CB, summing forces, what do we have? Well, we got all of CB plus BDY equals 0. Again, remembering that I'm going to plug in a negative 260 for BD, but I just need the y component. The y component would be 5/13, of course. So CB plus BD times 5/13 equals 0. So CB equals the negative of BD times 5/13. But the negative of BD would be the negative of 260 pounds, 5/13. And of course that'll end up being positive. The number comes out to 100 pounds for CB. You know what, I didn't include CB in my list, did I? 1, 2, 3, 4, 5. How did I do that? Oh, I got BD twice, that's why. I meant to put CB in here. There we go. Okay, so anyway, it came out to 100 pounds and it was positive, therefore this is a tensile load. So let's see if that makes sense intuitively. CB is here. The idea that we're pulling down on it, sure, that makes sense because this member BD is pushing against this and therefore also is pushing that point B downward. So CB has to be there to pull up on it and keep it from just falling apart. So that's it. We've got our table of loads in all the members, and that's what they asked us to find.